Hello students, welcome to the next lecture of the complex analysis. Today we will discuss about various examples related to the Cauchy Riemann and the analytic function. We are trying to explain you how you can check the analytic function with the help of the two different methods, and also we will able to explain how you can check the differentiability of the complex function. Myself Dr. Harish Garg. You can simply follow my YouTube channel where you can find the various lectures of the mathematics 1. So what we have discussed so far in the last lecture, we have discussed about the necessary and the sufficient condition that for the analytic function named as Cauchy Riemann equation. And right now we will see how we can check whether the function is analytic or not with the help of the several examples. The two methods which I explained little bit in the last video as well. The method one is if you take the partial derivative with respect to the z bar, if it is a 0, then it is analytic. On the other hand, if you take the partial derivative which is not 0, then you can say it is not analytic. That's one of the easiest way. Second method is you can find the value of the u and v, that's the real and imaginary parts, and satisfy these two properties, that is a necessary property, necessary condition, that's a Cauchy Riemann equation, and check whether the partial derivatives are continuous or not. Once these two properties are satisfied, then you can say the function is analytic. Let me quickly recall you how you can find the partial derivatives. So that's a partial derivative you can define. This is with respect to x. That means you have to keeping y as a constant. You can see y as a constant and changing the value of the x. And the difference of them will be here. You all remember how you can find the limit f dash as h approaches in a single variable. So you always define here divided by the difference of them. So here the same thing. We are keeping x, keeping y as a constant. This is the partial derivative with respect to y, so keeping x as a constant, and the difference of them is my here. Based on this, you can find, say, origin at the point origin. How you can define that? So this is my origin, x comma 0, 0. Y you can keeping as a fix, partial derivative of y, u with respect to y, so keeping x as a fix, and here. So based on these four properties, you can check whether these Cauchy Riemann equations are satisfied or not. And once you can see it is satisfied, and also check whether the partial derivative, whatever the answer you have obtained, are continuous or not. Whether they are continuous or not. If both the properties satisfied, then we can say it's an analytic. Make sure the first property, that is the Cauchy Riemann equation, that is this one, is only the necessary conditions. That means the existence of the derivative doesn't depend upon that. Or in other words, if you say the function is differentiable, then you can say the Cauchy Riemann equations are satisfied. That's true. But converse is not true. What is the meaning of that? You may have the Cauchy Riemann equation satisfied, but the function is not differentiable. It may happen because this is only the necessary condition. So if CR equations are satisfied, then the function may or may not be differentiable. So if the function is may or may not be differentiable, then you can say the function is may not be analytic. Remember, if you prove that function is analytic, this implies the function is differentiable. But converse is not true, as we already explained the various examples in our last lecture. You may follow my last lecture. This is one of the most important results. If you prove that the function is not analytic, how you can prove that function is not analytic? There is no need to check about the CR equation and others. You just prove that the function is not differentiable. Then it automatically implies that the function is not analytic. But if you want to prove that the function is analytic, then again you have to prove the two properties. The CR equation and the partial derivatives are my continuous. But for the not analytic, you simply prove that function is not differentiable. The question arises is how you can check the differentiability. So you have to simply find the limit. If this limit is my unique and exists, remember the uniqueness is the most important thing. Once the limit is my unique and its existence is there, then you can say the differentiability exists. But if the limit is not unique, if limit is my not unique, then you can say it is not differentiable. This implies function is not analytic. So this is a simple way you can check about their examples. So let's start with these various examples based on these phenomena. So you can see if you read the first statement, they are talking about examining the nature of the function here, including the origin. So nature of the function is you have to check whether the function is differentiable, you have to check whether the function is analytic, whether the function is continuous, and all about that. So that's a very simple, because this is the complex number, so you have to write this function in terms of u plus iota v. What is the u? That's a real component. I can write this separately. I can write as 5x over x raised to power 4, this is plus iota times x square y6 over here. Fine. So this clearly says this is my u if I compare this by here, and this is an imaginary component I call as a v. Fine. So this is my u and v. Now firstly we will check about the analytic function. So that means we have to check the two properties. First one is the CR equation, and second one is we have to check the partial derivatives are my continuous or not. What is the CR equation? Partial derivative with respect to x must be equal to the partial derivative of v with respect to y, and u of y is nothing but minus v of x. So the first way, either you can use this partial derivative, you can apply the u over v, but it will take a very lengthy calculation. The easiest way, we can apply this definition. Since we are using with respect to x, keeping y as a constant, so now you can substitute here. This is my u. I can substitute y as a 0, so this part will be 0. What is the u comma 0? So you can see from here u 0 0 is 0 and v of 0 0 is 0. So this is my 0 over x. So the right answer is 0. Similarly for this side, you can see what is the u of 0 comma y. So when x is 0, it's a 0, 0 minus here. Similarly, how you can define the partial derivative of v with respect to x? So keeping y as a fix, vary as a x. So we can take x on this v, I can substitute x as a x, y as a 0. So the limit will be limit x approaches 0, 0 minus 0 over x. Answer is 0. Similarly for the fourth. Now from here you can clearly say vx and this both are same, and they are negative of this, both are same. So you can see this equation satisfied, Cauchy Riemann equations are satisfied. The first property holds. Now we can check about whether these partial derivatives, partial derivative of u with respect to x and y, partial derivative of v with respect to x and y are both continuous or not. You can see that all are my 0, it's a constant function. Every constant function is a continuous function. Fine. Now we can check about the differentiability, because we have to find the origin. So f dash of here. What is the value of the fz? This is the value of the fz. We can substitute value here. F of 0 is my 0. I can substitute z as x plus iota y. So I can substitute here. Now I can change this limit. I can change, because now this is a function of the x and y. I can change this limit as x0 and y0. Fine. Now you can see this value will be cancelled out. So the remaining part is my here. Now how you can find the limits of this? So since there are the two variables, so you have to use the path test. So what you can do the path, that's again a very simple. Substitute denominator as a 0 in your rough side. Fine. What is the value of the y of 10 is minus x raised to power 4. Now consider this minus as a constant, as a slope, say m x raised to power 4. Or can you find the value of the y? So you can say y square is m y raised to power 5 is m square. Fine. If you take as a square root, or I can simply take m square and then so on. That's because m is a constant, there is no variable. So you can take the path y raised to power 5 as mx square. Substitute this value at here, value of y here, value of y here. Now you can find the limit. What is the answer of this? So x raised to power 4 is common from the numerator, x raised to power 4 is common from the denominator. So what is the limit? So which is here. Now clearly says it depends upon the value of m, and m is my slope which has the different value, so the limit is not unique. So once the limit is not unique, you can say limit is not unique, so it means the function is not differentiable. So as I told you earlier, if the function is not differentiable, it means function is not analytic. So that's a simple way you can solve the problem in such a simple way. So the function is not analytic inside the region including 0. Fine. Look at some more examples are there so that you will be able to understand more clearly. So show that the function is continuous. So firstly they are talking about the continuous, then CR equation and check whether y dash exists or not. Again the rule is similar. You have to find firstly u and v, open this bracket, so that's a x cube minus y cube. If I open this, plus iota as a common, x cube plus y cube divided by x square plus y square. This is my f of z. Now what is my u? U is the real component, so this is my u and this is my v. Fine. So you can find the u and v as here. Now firstly, because in last question does not involve the continuity, so how you can check about the u and v are continuous? So how you can prove? We all know for the continuity we always find the limit f of x and it must be same as that of f of 0. So here we are talking about the u, so we have to find the limit x approaches 0, y approaches 0, they must be same of this, but it will take a lengthy calculation. The easiest way we can see, whenever there is a term of x square plus y square, we can change into the polar coordinates. Fine. So how you can change the polar coordinates? We can simply check x is equal to r cos theta and y is equal to r sin theta. Fine. So if I substitute this value, what is my u? So u is r cube cos cube and here because denominator is my 1. Now you can take the limit as r approaches 0. So what will happen? What is it? Why r 0? Because we need x comma y as a 0 comma 0 and we all know r is here. So when x approaches 0, y approaches 0, what is my r? R is also 0. So what is there? When r approaches 0, what is the u? U is 0. V is also 0, whatever the value of the theta you have. It means u is independent of the parameter theta, hence the function is continuous. So the first part you can easily prove that it's a continuous. Now second part is you can check about the CR equations. So you have to check about here. We can check about the definition. We can take limit with respect to x. Fine. So keeping y as a fix. So y 0, 0 comma 0. So what is the answer of the u x comma 0? You can substitute here. So y is equal to 0, it will be cancelled. It will be here x cube upon x square, that is x. 0 comma 0 is my 0 over x. So the limit is 1. Fine. This is 1. Similarly, how you can define the limit? This is with respect to y. Y as a 0. So u keeping x as a constant and y as a here. So what is the limit of 0 comma y? So when you substitute x as a 0, it will be 0. This is 0, so answer is minus y. 0 comma 0 is 0 over y. So answer is minus 1. Fine. Similarly, you can find these other two limit. What is the v of x comma 0? So when y is equal to 0, it answer is x. V comma 0 is here. So the answer is 1. That is the limit x approaches 0. Similarly, when you take y as a 0, v of 0 comma y, answer is my 1 minus, sorry, it's a y cube. It's a y cube. So it's a y minus 0 over y. So answer is 1. So clearly says partial derivative of u and partial derivative of v both are same and they are of opposite sign. So therefore CR equations are satisfied. So once CR equation satisfied, then we have to check about the limit. We can start from here. What is the fz? Fz is my here. Fine. I can substitute this value. What is the z is? Z is my x plus iota y. What is my f0? F0 is given to you 0. I can substitute all values here. I can simplify the numerator, which can be written like here. Or if you think like, I can write this part for you. X, I can see is a x cube minus y cube plus iota times x cube plus y cube divided by x square plus y square into 1 over x plus iota y. Fine. Now clearly says there is no cancel about there. Now we can take the limit. So there are the two ways. You can take any of the path either as a denominator 0, or you can simply take firstly along the line, say if I take this as a 0, x square plus y square as a 0, so what is that? Y square is, okay, or you can say y is equal to mx. Simple, m is my slope, so you can either you can take mx or take y is equal to mx, that's on your choice. So y is equal to mx, if I substitute here, this value will be my, if I substitute this value, it is x cube 1 plus I minus x cube 1 minus I divided by 2x square, and this part is x plus I x. So x cube will be cancelled out, so the numerator is 2ix cube, 1x will be common, so it's a 2x square 1 plus x 1 plus iota x. So you can see cancel out iota over, what is the answer of this? So this is I over 1 plus I is the right answer. Fine. Now, sorry, it's 2 is not there, 2 is also cancel out. So this is a one limit. If you take along the other axis, say along the x-axis y is equal to 0, what will happen? If you take y is equal to 0, its part will be 0, this is a 0, this is a 0, so answer will be 1 plus iota. Fine. Third part, third thing, if from the both side you can get the same limit, but if I simply take y is equal to mx, okay, there is no need to solve like this way, you can also take y is equal to mx, substitute here, so what will happen? This is x cube 1 plus iota, y is m cube x cube 1 minus iota divided by x square plus m square x square into 1 plus x plus iota mx. So you can see 1x from here, x square from here, x cube will be cancelled out. So 1 plus iota minus m cube 1 minus iota is a 1 plus m square and 1 plus iota m. Fine. Now you can take the limit as x approaches 0. So the limit will be here. You can see again it depends upon the m. So it means the limit is not unique. So once the limit is not unique, it means the function is not differentiable. So once the function is not differentiable, this means the function is not analytic. So that's a simple way you can prove about that function. There is, if you take the two paths, we will get the same limit, but in journal we can see like this one. So it means instead of this, the function is not differentiable at 0. Okay, look at this another one. Show that the function is not analytic. So we can apply the first method is simple. We can write in the u and v. This is my u, this is my v. Check whether the CR equation satisfied or not. You can see here clearly says that the first property u of x is not equal to v of y because it's a negative. So what is the meaning of that? The CR equation is not satisfied. So once the CR not satisfied, the function is not analytic. Fine. If the CR equation satisfied, then we have to check that limit derivative. Otherwise, there is no need. As I told you, the second method, that's quite easy. You can clearly say what is the derivative of this with respect to z bar 1, which is a non-zero. You can write it directly as not analytic. Okay, look at this one. If the function is given to be here, prove that this, what is that? This is nothing but my f dash of z along any radius vector, but not 0 in any manner. So along any radius vector. Fine. What is the meaning of the radius vector is y is equal to mx. That is my radius vector. Any means we can take the denominator as a 0. So firstly we take about the radius vector means you have to find from this side. What is the equation of this is y is equal to mx. This is the radius vector. So if I substitute this value, what will happen? Here this divided by. So I can substitute y is equal to mx. So what will happen? Mx. So it is x cube mx. This is mx minus iota x, x raised to power 6 plus m square x square into 1 over x plus iota mx. Now since the function is complete on the x, so we can take the limit as 0. Now you can see from here x square, I can cancel out 1 x square and so you can write like here. Fine. Now you can take the limit as x approaches 0. So this part will be my m square. This is independent of x, and this will be my 0. So that means this limit will goes to the 0 along the any radius vector. Fine. Second part he said, but not 0 in any manner. How you can prove that in any manner? You can take the denominator as 0, find the value of the y square is. So just ignoring this negative sign, you can simply say x cube. Fine. So and this is my representation of the slope. So if I take this path, y is equal to mx cube, or if you simply take x cube, that's also fine. But if you want to take y is equal to mx cube, that's also fine. So again we can substitute here. This is my f, this. So I can substitute y is equal to x cube here, here, and divide it by this. So you can see this is x6. I can take the common as x6, cancel out. You will get this expression. Now you can take the value as x approaches 0. So this part will be 0, minus iota 1 plus 0. So clearly says it is minus iota over 2, which is not 0. So you can see which is not goes to the 0. Okay, so you can see therefore the limit is not 0 along the any path except the radius vector. So when you take y is equal to mx, then only it's a 0, but on the other hand it is not a 0. Okay, look at this another result. If f is my analytic function, it is already given that analytic function, it means these properties hold. It is already given to you, and the modulus of this. Okay, so if I have f is u plus iota v, what is that? This is nothing but my real square plus imaginary square. Then you have to prove that, and this is my constant, say k. Then you have to prove that f is my constant. Okay, very good. Or in other words, you can say the analytic function with the constant modulus is a constant. Proof is very simple. If I take f is my here, which is analytic, then mod of f will be my here. Fine. You can write as a square root as well, no issue about this. So given that mod of f is a constant, so I can take as a k. Now what is given to you is analytic. Your target is to prove f is constant. So remember, f is my u plus iota v. So if I prove that u is my constant, v is my constant, so then definitely this implies f is my constant. Fine. So now your target is to prove u is constant. So when the u will be constant, when you take the derivatives, it must be 0, or derivative with respect to y is a 0. Then only you can say it's a constant. So do you think from where you will get partial derivative of u? And so that is based on the analytic. So if firstly if k is equal to 0, so then u square plus v square is my 0. Fine. The square of the two value will be 0 only when both are 0. So when v and u both are 0, so f will be my 0, which is a constant. Second case, when k is my non-zero. So once the k is my non-zero, then you can partially differentiate this with respect to x and y. So firstly I can take the partial derivative with respect to x. 2v partial derivative of, because k is constant, is a 0. And if you take the partial derivative with respect to y, this is y plus 2 times v over here. Fine. Now you can clearly say if I divided 2 is a cancel out, which is written here. Substitute the Cauchy Riemann equation. What is that? We all know, because f is analytic, so this equation satisfied. Fine. So I can replace the value of the v as u, and we also know partial derivative of this is v with respect to x. So I can substitute this value v with respect to x and here. Now if you solve them, can you solve them? How you can solve? You can add them. No, if I subtract them, fine. If I subtract them, you will solve them as of this method. Fine. Or otherwise you can simply solve this. So you can see this is number is my k, which is a non-zero. So what is the meaning of that? Partial derivative of u with respect to x is my 0. So what is the meaning of that? If partial derivative of u with respect to x is 0, can I say partial derivative of v with respect to y is also 0 by using CR equation. Fine. So once the partial derivative of u with respect to x is 0, I can substitute here. What is the meaning of that? V with respect to x is also 0. So what is the meaning of that? From these two equations, we can say u is a constant with respect to x, v is a constant with respect to the x. So now we can use the partial derivative. What is that? Because the function is analytic. So here, what is that? This is 0 plus 0. So the derivative is my 0. So whose function is derivative is 0? What is that function? That is my constant. So what is the meaning of that? That's our required target. So that's a simple way. Otherwise, you can also prove that the u is my constant, v is my constant. That's also you can prove that from here. That we will see in a couple examples. Fine. Okay, look at this another one. Consider the function here. Show that the CR equation satisfied, but the function is not differentiable. It means your target is to prove function is not analytic. Remember, if not differentiable implies not analytic, but converse is not true. Okay, so for the CR equation we need of this. So firstly we have to find the in terms of the u and v. I have to express this value as of here. What is that? This is x minus iy over x plus iy. Fine. So I can rationalize them because complex number is written in the denominator. I can return I of this. So the numerator part will be cube divided by x square plus y square. Fine. Now I can open this bracket, a cube, a minus b whole cube. Fine. And I can break them as real component separate, imaginary component separate. This is my u and v. Then by applying the definition of the Cauchy Riemann, that is by using here, so we can find the limit x approaches 0. So what is that? In the u, y is 0. So this part will be 0, this part will be 0. The answer is x. What is the u comma 0? So this is already a 0, 0 is given to you here over x is my 1. Fine. Similarly, you can define this value. So limit y approaches 0, 0 comma y. When x is 0, it's a 0. This is also 0. This is 0. This is y. So it's a 0 minus 0 over y is my 0. Similarly, for the other two part, we can find I here. So clearly says this limit and this value both are same, and these two are of the opposite signs. So you can see this property satisfied, Cauchy Riemann equations satisfied at the origin. Second, you have to check about the differentiability. So we can start from here. I can substitute the value. What is the fz? Fz is my mod z square. F0 is 0 divided by z. So I can return this number as of here. Substitute this value. Now you can take the path. There are the various ways. If I take along the path y is equal to 0, that is along the x-axis. Along the x-axis y is equal to 0. What is the answer of this? 0, 0, it's a 1. If I take along this side, x is equal to 0. When x is equal to 0, answer is again plus 1. But if you take along any other path, y is equal to say x, the answer will be, when you take x, y is equal to x, y is equal to x. So x will be cancelled out. 1 minus iota or 1 plus iota square. So clearly says that all the limits are not same. Otherwise, the second method you can simply take the denominator as a 0. Fine. So the path will be by y is equal to mx. So I will show you the both case. So along the x-axis, that means y is equal to 0. Answer is 1. This is also 1. And on this side, it is a 1 minus iota over 1 plus iota square. So what is that? If I open this, a square plus b square minus 2ab, a square plus b square plus 2ab. So what is the iota square is minus 1, it's a cancel out. So minus of 2 iota, this is cancel out, it's a plus of 2 iota. So answer is minus 1. And you can see all are not same. So limit is not unique. Fine. Otherwise, you can simply take the path y is equal to mx. So this limit will be my x minus iota mx, x plus iota mx. Fine, limit x approaches. So x will be common, cancel out. So 1 minus iota m, 1 plus iota m. So clearly says that it depends on the m. Fine. So it means for the different value of the m, you have the different limits. So limit is not unique. So once the limit is not unique, it means the function is not differentiable. Hence the limit does not exist. So once the function is not differentiable, you can say f is not analytic. Look at the another question. So for what value of the z the function is ceased to be analytic? So you have to apply the condition on the z so that this function is my analytic. That's a very fine. So what is the property of the analytic? You have to just simply check about the differentiability. So we can start from the first part. This is given to you. So I can write these terms. I can write firstly find this value. W is nothing but my function. Okay. So it means I can write firstly W in terms of Z. I can start from here. So we can write like here. We need to find this value. So start from here. How I write this part? So this part is nothing but my, from this I can written like here, because by using the log property, W I can written like here. So I can substitute the value of this. What is the value of this? E raised to power iota phi is e raised to power z. I can substitute the value here. So what is my W? Is e raised to power z. So once you know, can you find the derivative of this? Here. So now you can tell me at what point of the z this value goes to the infinity. It can never goes to the infinity. Fine, only when z is infinity, but z is here. So you can see this is, so function is analytic only when this is my phi. So hence function is said to be analytic when this row, because this goes to the infinity when z is infinity. So we have to just simply think about that. When this row is a finite, then we have an analytic function. Look at the second question. Again in this question we need to find the value of this. So if you look about this term, it is just like say sine of a plus b. The only difference is in terms of hyperbolic. So we can apply this. What is that? This is sine hyperbolic u sine a cos b plus cos a sine a. Fine. Now the thing is, what is the sine cosine hyperbolic? So that is the simple rule. So since it is a sine, so instead of open this bracket, I can simplify like of this manner. Fine. Now I can open this bracket. What is that? This is sine u minus, sorry, iota v u minus of v. Fine. I can written like this way. Now you can use this formula as sine of a minus b. So I can open this value here. Now I can open this minus bracket also. Sine of this by using this property is iota times. Now I can multiply this iota here. It's a plus of this. Now you can see this is same as that of here. So this is nothing but my z. And what is that? This is w. So that my sine hyperbolic. So what is the value of the w? Is sine hyperbolic inverse of w. So we can find the derivatives, which is here. So this function will be analytic when this part is a non-zero. That is, whenever z is plus minus iota, then the function is not analytic. Otherwise, yes. Okay, look at this another one. A function is given to you. Prove that the function is constant if any one of the following properties holds. Okay, so firstly we assume this is here, then we prove f is constant. So given that a function is analytic, it means it satisfies the CR equation. First part, f dash 0. What is the definition of the f dash? This is the property of the f dash. If the function is analytic, how you can find the derivative? This is the rule, v with respect to x. Okay, or I can replace this v with respect to, or I can write in terms of the u only by the CR equation. So this is 0. What is the meaning of that? I can written this as here, equating the real and imaginary components, you will get here. So what is the meaning of that? U is constant. Fine. Also, by using the CR equation, if curly partial u by x is 0, so it means partial v is 0 and partial v with respect to x 0. So from here you again got as v is my constant. So from both the case you will get u and v constant, hence f is my constant. The first part is proved. Look at the second part. Consider that the r is the real component, real part of the z. So what is the real part of the f is u. So u is my constant. Then again your target is to prove f is my constant. So if u is my constant, partial derivative 0. Apply the CR equation again. So this is v with respect to y is 0 and this is minus v with respect to x is 0. So what is that? Both are 0. So v is constant. So from here you will get as a v as a constant. So u as a constant, v as a constant, it means the function is constant. Third part, when imaginary part is here, so that's again similar. Now you can start from here. So again by using the Cauchy Riemann equation, you can say this value is 0 and this value is a 0. So from here u as a 0 or u as a constant. So both are this one. The last part is argument. So how you can define the argument is tan inverse y over x, but here is a v. So instead of the y and x, we call this as v over u. This is my argument. So can you find the value of p? So it's a v over u is tan of k. So I call as another constant c. So v is nothing but my this, or you can say another constant c. Now you can see v minus uc, which is nothing but the real part of c plus iota. Why? You can see this is my here. So if I open this bracket, it's a uc and this is my here. This is my real component plus iota times complex component vc plus of u. So this is my real component, and which is a constant. 0 is a constant. So by the second part we can see this is a constant. So c is also a constant, iota is a constant, it implies f is also a constant. Okay, look at the last example. Consider the function here which is not analytic. Show that although the CR equation satisfied. Fine. So firstly we can start from here. We can compare this with the u and v. This is u and v. We can apply this definition. I can show you the one, rest you can do it by own. What is the u x comma 0? So y is 0, 0. So the answer is 0. Similarly you can find for the others 4, you will get as a 4 zeros. So clearly say this property is satisfied. Once this satisfied, it means CR equations satisfied. So this properties hold. Function is not analytic. So basically your target is to prove the function is not differentiable. So we can start with the f dash z and we will check whether it's depend upon the limit is unique or not. So we can substitute this value here. Now how you can do? We can take the path y is equal to mx. If I substitute here, which is limit x approaches 0, this is of mod x m x square, 0 is 0 over x plus iota x. Now you can see x I can take as common from the numerator and x can be taken common from the denominator. So the numerator part is my mod of m and this is 1 plus iota m. So the answer of this is this divided by 1 plus iota. Clear? So which is again dependent upon the value of the m, which is not unique. Once it's not unique, it means the function is not differentiable. So function is not differentiable means function is not analytic. So hence you can say these properties hold. So I hope you can simply learn the various concepts about the examples of the Cauchy Riemanns and the other things. We will see the next lectures on the harmonic and the conjugate harmonic functions related to the complex analysis. Till then, you can simply like, share and comment my video. Best of luck students. Happy luck.